we have a new problem. This time we have a tendon. So it's has a length of 15 centimeters, and we can always change that to meters if we wanted to for convenience. So we'll do that right away. So 15 centimeters to become meters, you change that by using unit conversion. 1 meter is 100 centimeters. So this is equivalent to 0.1 meter, or rather 0.15 meters. The other thing that happens is that the tendon happens to be stretched a distance. So this is kind of like the new length. So initially it was at this point, and then it got stretched distance of 3.7 millimeters. We can change that to meters right away by saying, first of all, do a conversion from centimeters, or rather from millimeters to centimeters. So 1 centimeter is 10 millimeters. And then after that, do a conversion for centimeters to meters. So that's 1 meter over 100 centimeters, or rather 1 meter over 100 centimeters. So we end up with 0.0037 meters. You can see we have 3 zeros right there, and that just means that we're going to be moving that way. So 1, 2, and 3, and you end up with 4 significant figures right after the decimal place. So it's stretched. This tendon is being stretched that way, a distance of 3.7 millimeters. The force responsible for the stretching is equivalent to 13.4 newtons. That's the force that's doing the job. And then we're also told that, this has a diameter, the tendon has a diameter D, equivalent to 8.5 millimeters, and we can always change that diameter D into meters. So D equals to, we'll assume the stretch is, you can call it delta D if you wanted to for convenience. So this one is 1 centimeter over 10 millimeters. And then we have 1 meter over 100 centimeters. This gives us 0.0085 meters. That's the number that's given for the diameter. And if you also wanted to go ahead and find the radius, you'd have to divide that value by 2. That's the radius. If we divide this by 2, we end up getting the radius being equivalent to 0.00425 meters. So these are convenient numbers that we're dealing with. It's going to be helpful in solving the problem. So that's the information we're given. The goal of the problem is to make sure that we find what we call the Young's modulus of elasticity. So that's modulus of elasticity is used to look at the relationship between stress and strain. So we use a Y, stress over strain. That's the Young modulus of elasticity. When a tendon like this is undergoing some type of stress, the responsible element for the stress is the force, and we're seeing, okay, so what's the force causing this stress and what's the area that the force is acting on. Remember, if we're going to have to find the area, the radius comes into play. Area is pi r squared, as you can recall. The other unit, the strain, we just define that as the change in length. We call that delta D, if you can recall, over the original length, and we call that D. So given these two pieces of information, we can combine them in the formula and end up solving for the Young's modulus. So we have stress over strain, and we define stress as the force over the area. So F over this F over A, and then this one is delta D not delta D though. The original length was 15 centimeters. So we're going to call that L, just to clarify. And then instead of calling the change in length delta D, we're going to call that delta L, just to distinguish it from the D, which is the diameter. So going back, we have instead of calling this delta D, we're going to call it delta L, all over the original length, which is L. Now we are at a position to plug in the specific numbers in the problem. So this becomes, we can rearrange the problem, or we can plug in the numbers right away. I think it's helpful to rearrange the problem. So this one means that the force, the original length, comes at the top, and then we have delta L in the denominator and the area. So the force itself is 13.4 newtons. The original length, we already did a conversion to meters, so 1.5 meters, and it's helpful to do the conversions because that helps with the cancellations. So pi, this is the area, is pi r squared. The radius was 0.00425. So, just to recall, this is pi r squared. And so delta L, coming back here, is 0.0037 meters. And the area is pi times the radius, which is let's just go back and see, it's 0.00425 meters, 0.00425 meters, and then that has to be squared to get the overall area. So with the Young's modulus simplification, we end up finding that it's round about 9.57 times 10 to the 6 Newton per meter squared. These units, Newton per meter squared, are also common for pressure, but in this case, you're dealing with Young's modulus of elasticity. So I think the key part of the problem is making sure that your conversions are right, and then having the appropriate formula, stress over strain, defining stress in terms of force and area, and also strain in terms of change in length and the original length. I think we can add length right here, just helpful. And then we plug in specific numbers that represents the variables that we're dealing with, the force, the length, the change in length, and the area. And then we get 9.57 times 10 to the 6 Newton per meter squared. So hope you enjoyed the problem. Feel free to send any questions and comments, and have a wonderful day. Okay, thanks. Bye.